Yeah, wonderful. Okay, our next speaker is Tzeng. You speak alone.
Excuse me. Just to intervene, we have no sound on the Zoom. If we could kindly fix that. Excuse me. Just to intervene, we have no sound on the Zoom. If we could kindly fix that.
Est-ce que c'est toi?
Oui.
C'est bon. Un recording que tu écoutes?
Non, c'est live. C'est YouTube en fait.
Mais tu as parlé.
Oui, moi j'ai dit parce qu'il n'y a pas de son de speaker.
Ça a parlé, mais tu n'as pas parlé ici.
Oui, parce que j'ai regardé, j'ai mis le Zoom, YouTube.
Je comprends rien.
Alors,
specifically the non-Hermitian type of entropy and the Tzeng entropy have a lower scaling. Yeah.
It's not working. Use my testing. Turn off the volume. Testing. That.
Can you turn off the sound?
Turn off the sound.
No, just mute the sound.
The volume. Testing. No, you're still getting sound coming out. The volume of your speaker, it outputs sound. You need to turn it off. Testing.
Yes, I can hear you perfectly fine. Maybe one solution could be if your computer is somewhere close enough to
Yeah,
you.
we're doing that. But the fact you can talk out of that one means that there's.
The sound off.
You need to turn your volume on.
I will turn off.
Yes, to turn the speaker volume off as well. The speaker.
Testing. No.
Now try.
Testing.
Yes,
That's good.
better.
That's good. Okay.
Keep going now. We put a microphone on here. So.
Okay.
Yeah, just keep going.
For the non-Hermitian system, we define we need to. For the non-Hermitian system, we need to have a little bit modify the definition of fidelity because the eigenstate is classified by the left and right eigenstate. And then after this different, after modify a proper definition, we find the fidelity susceptibility can also can detect both the quantum critical point and the exceptional point. And also the entanglement entropy need to slightly modified since the reduced density matrix now is no longer Hermitian, it's a non-Hermitian. This implies the eigenvalue of the reduced density matrix is complex number. So we define a proper non-Hermitian entropy this and also the very version type range entropy, and then we found it is also present a log scaling in the 1D critical system, where the non-Hermitian quantum critical system is described by some non-unitary CFT field, CFT, and the sample charge can be negative. And we found that this definition can be used for extract the negative central charge. And it has been also studied by characterized groups and by the symmetry result of the entanglement of this entanglement entropy, and then also they can find the central charge for the non-Hermitian quantum critical system. And for the gap system, recently I calculate the spin layer, non-Hermitian spin layer, and then and compute the momentum result entanglement spectrum. And for in the Houghton phase, this is a symmetry protected topological phase. So and then in entanglement spectrum, for the real part of the entanglement spectrum, you can find there are two parts. One is the CFT-like entanglement spectrum. You can count the state by 1, 1, 2, 3, 5. And then the other part is the gap non-CFT portion. There's a finite gap. Okay. So now today.
How can you separate out the gapped non-CFT from the gap plus CFT just by eye?
For example, okay, this is the momentum result and also magnetization result.
I see.
Okay, so you look at this by, for example, you focus on this circle. This
yes.
Is
empty equals 0.
Okay.
I see.
You want symmetry or the charge sector for one charge sector, and then so you can see on here is one on the linear shadow in the linear shadow is 1, 1, 2, 3. Okay, this is the counting, but here you don't have this state. This is the lowest state here is separated by the pi here, so you can distinguish because they have a pair. They have
the quantum. So, thank you.
Yeah,
okay.
so you can have you can distinguish.
Okay.
Safety part and non-safety part. Okay. And all the different U1 sector have the same thing. Okay. But
good. That's fine.
I'll focus on the fidelity today.
Okay. Great.
Thank you for this question. It is very interesting. Okay, so I want to talk how to get a non-Hermitian Hamiltonian. One possible there are a lot of possibility to get a non-Hermitian system. For example, if you consider open quantum systems, usually the density matrix of the system is described by some master equation. Take the Lindblad equation, for example, and this is the Lindblad equation. Some people claim, or in the short time evolution, this part can be ignored. Then you absorb the other part into the system Hamiltonian, it becomes a effective Hamiltonian, and this effective Hamiltonian becomes non-Hermitian. So in this way, you get a non-Hermitian Hamiltonian with the gain loss type, gain and loss. For example, L can be a creation operator or an annihilation operator. Then this becomes a density operator, and you can also get a non-Hermitian Hamiltonian from Green's function or other theory, and also for the many years ago, people or in a statistical mechanics model, people already study a lot of non-Hermitian systems like beyond edge singularity. They have a central charge equal minus 22/5, and or like the Q-deformed XSD model, and also non-Hermitian asymmetric SSD model. These two models can be solved by beta ansatz. When this model can be, you can consider this, if it is in open boundary condition, then you have the gain and the loss on the both sides, and it is become non-Hermitian, and depend on different parameters, and you can have a different central charge from 1 to -2, and we use the new defined entanglement entropy, for example, the Boltzmann type entanglement entropy, and then we can extract the correct central charge on this model, and finally, if for example, people, it is the old paper, people consider the classical and quantum correspondence, and then for this model, here this phi is a real number, so this is non-Hermitian. Like the hopping to left and the right are imbalanced. It is similar to yesterday. Yesterday's talk about the Hamiltonian model, but this is an intelligent model. Okay.
Question. If I solve a non-Hermitian model by the beta ansatz, do I have to have a sort of separate ansatz for the left and the right? And anybody
I don't know how to solve the beta ansatz, but they solve the beta, they solve the model by the beta ansatz equation. Yeah. And yeah, in single particle picture, if you turn this delta equals 0, then or you can I did a exact diagonalization numerically, and then I found the energy spectrum is like a ring, so it is consistent with yesterday I have done did a point gap spectrum. Okay. Okay. Besides the non-Hermitian scaling effect, there is also another very important part that it calls the exceptional point that do not happen in the Hermitian physics. Okay, so we know for the Hermitian operator, the different eigenvectors with different eigenvalues are orthogonal. In other words, the non-Hermitian, the eigenstate is not orthogonal. Suppose we have a parameter gamma is tuning the non-Hermiticity, then gamma equals 0 is the Hermitian. So these two stay different. This is one state and first recited state are orthogonal. Then when gamma is not 0, then it is not orthogonal. And then we continue to tune the parameter. And then finally, we find it become merged together, and we call this is the this looks like the degeneracy, but the degeneracy is called two or more eigenstate have the same eigenvalue. The eigenstate are still not the same, but here it is better call less, because two or more eigenvectors merge into only one eigenvector. So we call this parameter point is the exceptional point. At this point, eigenvector is all the eigenvector cannot form a complete set, and this is already found in a lot of experimental system. And for example, people find close to the exceptional point, the sensibility can be enhanced greatly. Okay. So I'm talking about the fidelity, and before I talk about fidelity, I want to quickly review about what we have done in the product. We all already know the inner product from high school. This is what we learned, and then in quantum mechanics, we need to define a cat space, and then we define the dual correspondence space is the cross space. And then the inner product of these two the two states take another vector in the cross space and then do the multiple and then the sum. And we also learn another inner product from the relativity. We know that there is a G mu is the metric of the space-time, and x is the flow vector, and flow vector, and then we should consider a metric in a curved space. How to do the inner product? We need to consider add the metric tensor. Now the non-Hermitian quantum mechanics, we can generalize we have a cat space, and then by the broad space is dual correspondence is you take the broad and then you need to multiply a metric tensors. So some people already use this perspective to prove the non-Hermitian novel theorem in quantum information. Okay, so it is consistent with the bi-orthogonal basis. Since Hamiltonian played a role in the evolution, so and the Hamiltonian is known as non-Hermitian, so the H and the H dagger play a role in the evolution. So you have two different kind of scheduling equation. One is the H and another is the H dagger. So how we do this in exponentially on the exponential of operator? We need to do the Taylor expansion. So eventually we need to have the power of matrix, and then we need to diagonalize this. So we look at eigenvalue equation of this, and we multiply V inverse on the left both sides, and then it becomes and then we remove the V here, we get another eigenvalue equation. Then we collect the V, the eigenvector here, we can call it, this is the right eigenvector, and V inverse is the left eigenvector. So satisfy the right eigenvalue equation and the left eigenvalue equation. They have the same eigenvalue, and since V and V inverse are inverse matrix for each other, so you have this bi-orthogonal condition. Okay, so and this is equivalent to if you like this geometry perspective, and then you can choose the matrix become a sum of all the left eigenvector, and then this in most cases they are equivalent. Now we already know how to do the inner product. So in the Hermitian case, the fidelity is defined by this way. So now we know in the non-Hermitian system, the broad should be multiplied by its metric is right multiplied by its metric. Or in the bi-orthogonal basis, we take the left and right. This is our definition of the fidelity, and then if you okay, and there are other definition they propose, but we found that our definition has general property with PT-symmetry. First one is when the system is in a PT-unbroken phase, the fidelity are real, and then approaching to the exceptional point, the real part of fidelity susceptibility approach to negative infinity. And you can if one of the states in the PT-unbroken phase, another stays in the PT-broken phase, we found that fidelity, the real part of fidelity itself is one half if it is a second order exceptional point. So after we have this property, we can do some scanning like this. When these two states when the lambda EP is between these two states, then we can find the real part of fidelity equal 1. Finally, I give some example of the fidelity susceptibility. One is the SSD model with the gain loss type. You can think that this is like a Swift-Hughes model with the interaction, and by using the either diagonalization, and we find the fidelity susceptibility goes to real part of fidelity susceptibility goes to negative infinity, and then when the exceptional point is between the two states, the real part of fidelity is 1/2. And another example, we use the fidelity to support the AKOT model is robust, and it's not it still remain the topological system in the if we just add a small non-Hermitian term, then the fidelity susceptibility do not go up to positive infinity or negative infinity. So it means there is no quantum critical point or exceptional point. Other example, people already generalize to some non-PT-symmetric Hamiltonian. Okay.
Is there a reason why you take this particular non-Hermitian conjugation? It looks quite peculiar.
Because we want to add it on the edge, but if we only have the two SZ, then it breaks the time reversal symmetry. So we want to have the time reversal. The time reversal symmetry change the sign U as I. So and SZ should be a number of SZ should be R. So we choose this particular non-Hermitian is PT-symmetric non-Hermitian perturbation. Okay, so this is my final slide. To compute the fidelity, you only need a ground state, so it is very convenient. If you work on any kind of numerical method on many body interacting system, maybe you use length sources iteration like I just showed you the result, and or you study DMRG or any kind of metricized state or tensor network algorithm. It is relatively easy to get only ground state. Now, if you want to study non-Hermitian system and you use numerical algorithm for a very complicated system, then you can compute fidelity. And compute fidelity, you only need the ground state. Okay. Thank you.
we're running a bit late, but just one or two quick questions. Yes, Chris.
Can I ask you a question about your definition of the fidelity? So you pointed out that an advantage of this definition is that for PT-symmetric phases, it's real.
Yes.
And I know that for PT-symmetric Hamiltonian, it's the eigenvalue. Is there a relationship between these statements?
The PT-symmetric Hamiltonian, the eigenvalue in the PT-unbroken phase, the eigenvalue are real. Yeah, that is true. That, but eigenvalue, so you ask me eigenvalue.
So my question is, you've made a statement of fidelity.
Yes.
I also know that the eigenvalues for Hamiltonian.
Eigenvalue of harmonic. Yeah, yes, right.
Is there a relationship between those two? We put this property only use the PT symmetry, but we didn't use the eigenvalue is real. Yeah. But they can have maybe some relationships, but we didn't use these properties.
Yes.
Quick question. So we showed these central charge values, and to the integral values of central charge correspond to some gapless mode in non-Hermitian systems also.
Like this.
Yeah, so like when you have this constant value one, does that correspond to some gapless mode, like it corresponds to Hermitian systems? Or?
The central charge is here. This two model is gapless model. It is already in the critical point. So and then it is 1D, so we can describe by some safety. But here for this one, the safety theory is a non-unitary safety, and then the central charge can be negative.
But when it's when the central charge is one, it's when the central charge is volume one, it's there, it's still non-unitary.
When the central charge,
so it's non-unitary throughout, like regardless of what's the value of the central charge.
this is the central charge. For example, this is for the theta equal pi over 4. Then the central charge is 0.5, and the central charge is the theta equal pi over 2. The central charge equal -2. And this line is predict the previous result, and the red data is our result by using the entanglement entropy scaling.
Okay, I think we'd better move on. We're now 25 minutes late. We will have 20 minutes for coffee, unless you don't have too much for a train, do you? No, okay, 20 minutes for coffee, so you have time to get coffee, but please be back promptly at 4:15, which is exactly 20